So welcome everybody to Construction Tech today. We're very excited to be presenting or to have a presentation with Gary Klein, who is in hot water. The Passive House Accelerator is a collaborative online platform for sharing innovation and thought leadership in passive house design and construction. We publish articles and interviews, produce weekly virtual confabs with passive house pioneers from around the world, and elevate the work and programming of the passive house movement's leaders, practitioners, and organizations through interviews, articles, social media campaigns, video, and podcasts. Our aim is to catalyze zero carbon building by accelerating the adoption of passive house building. With our co-hosts, Kevin Brennan, Shannon Pendleton, Sean St. Amour, and Mark Willey, we produce Construction Tech Tuesday to share the technical, the technique, and the technology of passive house construction. Each week, we welcome guest practitioners to dive into the details of practice with the builder and tradesperson as our target audience. We welcome folks from all corners of the construction and design world to join us each week, and we're really happy you're here today. Thank you.
Hey guys, I'm Kevin Brennan. I'm from Brennan Insulation and Air Tightness here in New York City. I'm very happy to have Gary Klein on the show this week. He was previously practically on the show when we had Adam Romano on, and we were talking about passive house hot water with those systems. And it's always been a great pleasure to run in and learn from Gary when I'm at summer camp, which I haven't been to in the past 2 years. But he's a wealth of knowledge. He shares so much, and he's so well educated on the topics. It's you hold on to your seats. You guys are going to be blown away by the presentation. And my personal view is the gains we have to do in passive house is in hot water. There's a lot of innovation and a lot of improvement. By including the envelope means that we have a lot of space there.
I couldn't agree more, Kevin. Thank you so much for adding that. I am excited for tonight's presentation. I'm Shannon Pendleton from Sanderson Design, zooming in from New Hope, PA. I want to remind everybody to open up the chat window, and when you put a question in there, put a Q before it, and get ready to talk about reducing costs and operating expenses and energy output for our project with Gary tonight.
So thanks, Shannon. So just before we turn over to Mark and Gary, I just want to say a big thank you to all of you that show up, but I also got to thank my lovely co-hosts and the rest of the Accelerator team, because behind the scenes, there's a lot of things that go on that you guys don't get to see and hear. But I tell you, this group that I get to hang out with all week long as we plan and prep and is amazing. And honestly, we have a lot of fun. Like literally, they have put the capital PH in fun. And so I enjoy hanging out with this group. And then all I have to say about Gary, and I hopefully don't take away the thunder from Mark, is sit down, enjoy this next little bit, and also plan later this week when Zach sends out the video to plan to watch it again. Because even in the run through last night with Gary, he just drops nugget after nugget after nugget. And so this, again, as Kevin said, this is an area we don't dive into too much. We are in for a treat. So be present, put your ears on, and sit back and enjoy. And thanks for showing up.
Sean, the message about the orange shirt is great. For everyone that didn't hear, right when Kevin finished his speech, the bell went off. So that means he's on a fire call right now. So Godspeed to him and the crew. My name is Mark Willey. And I have to say, at some point in your life, you may be blessed with being able to share a dinner table with Gary Klein. That happened to me in Chicago many years ago. There's a bunch of folks from the Passive House group that sat down for a dinner. And I'm going to give you a fair warning. If you have a chance to have dinner with Gary, don't order any food, because you won't eat it. You're going to spend the whole time listening. You can't stop to chew because you might not hear what he says. And his plate's going to get cold because he's talking the whole time, and he ends up taking it to go. So it's important to treasure the moment when you're with great people in the industry. So I'm looking at my phone so I get this right here. So the International Association Plumbers and Mechanical Officials, well, they recognize Gary. I can't say that's happened to many other folks in my life. That's pretty powerful. Also, we have the Department of Energy has recognized Gary. Of course, he did spend a long time working with the California Energy Commission. And you'll find throughout his presentation today that he may have also worked on other continents for a period of time. We all have water pipes. We're going to find out that they can't read very well. And our speaker's often in hot water. So why don't we see if we can get him out of hot water. Gary, welcome to Passive House Accelerator Construction Tech.
Thank you very much. So as you know, Mark, that I didn't make it to my home base for this conversation. I am parked near a Target somewhere in Vallejo, California. And hopefully this is coming through loud and clear. Are we good? All right, so I think we should just get started. There are two kinds of questions, but put both in the chat. There are clarifying questions, and someone's going to watch the chat box for those. And there are exploratory questions. Clarifying questions we will attempt to take close to the slide on which they occur. Exploratory questions we'll take at the end. And I will stick around afterwards for extra time or overtime, whatever we call that. Are you all ready?
I just want to brief Shannon, Gary, with that. So Shannon, at times he's going to ask a question, and both you and Sean and myself can answer that while people answer in the chat. So Gary, beautiful background behind you. We can't even hear the wind of the Pacific. Love that. Great background.
If I'm near the Pacific, we're in big trouble, let me tell you. All right, so tonight the title is pretty straightforward. Reducing time to tap is just the tip of the iceberg. In the last year and a half, I've been working on multi-family apartment buildings around the country. Most recently in upstate New York, we built 3 buildings this past year based on our plumbing designs. And as many of you know, I've been working on this question of how long does it take for hot water to arrive at the furthest fixture in your house for over 30 years now. And you know what? We know how to solve that problem. It has to do with the volume of water in the hot water pipe between the source and the use. That's the only way to solve the problem. Less volume, less time for a given flow rate. That's it. There's no other ways I know of to do it. And so that's an architectural decision as much as a plumbing decision. And we're going to cover that a bit tonight. But during this past year, I got involved in right-sizing the plumbing for multifamily apartment buildings. And that's what I want to talk with you about tonight. And I'm going to say that better floor plans lead to better performance, and we'll discuss some of the implications of that. Tonight's presentation is really a starter in a series, because if tonight doesn't capture your interest, then you really don't need to know how to do it. Tonight's going to talk about the why and what it means for the benefits for the builder and the consumer. All right, so what are we aiming for? I think it's important to know where we're headed in order to know if we arrived. And I would suggest to you that people want a few things. They want the water flowing from their showers and faucets to feel right. At any flow rate, it has to feel right. You know, you want your toilets to flush first time every time, not first time, second time, third time's a charm. You want it to work right. You want clean dishes, clothes, and bodies, and you want the service of hot water as efficiently as possible because you don't want a big bill for this service. We're used to set it and forget it, every 12 years replace it. That's the business model for water heating. I don't think that's the right business model, but it's the one we have. And even though I used to work at the Energy Commission, I don't think it makes any sense to discuss efficiency until the desired service has been provided. Because I don't really care if it's efficient, but it doesn't work right. I'm sorry, consumers will tear that out in a heartbeat. How big is hot water? Well, it's the first or second largest single family residential energy use. And in passive homes, it's even bigger as a percentage because the envelope and the equipment is so good, right? So as was said earlier, this is a big deal. And so this percentage you see down here in passive house has got to be closer to half. The pie itself is smaller. All that's true. And so in multifamily, it's an even bigger percentage and even more so in passive house multifamily. Again, the envelope is trivial in the scheme of things because there's fewer exposed walls to begin with per apartment, and the buildings is easier building. And I would say that we've made great progress in pretty much everything except the efficiency of water heating since I've been involved for 40 years now. Fair enough? And I know we've got recent experiences with, heat pump water heaters, and before that, gas tankless water heaters. And the answer is, that's nice. We still haven't figured out how to integrate them into the architecture very well, and we're still on a very steep learning curve. So let's keep moving. So the first thing I want to talk about is reducing the time to tap. The key in reducing time to tap is that you increase customer satisfaction. Why? It takes less time for hot water to arrive at your fixtures. So how long do you think you should wait for hot water to arrive? Anybody want to hazard a guess? What do you think? Anyone want to wait at least 5 seconds? Want to wait no more than 5 seconds? Raise your hands. Okay. How about no more than 10 seconds? How about no more than 30 seconds? Still going up. You want to go 10 seconds? You're raising your hands, Sean. I don't know what to do with him. So look, the dilemma is this. People don't really want to wait very long. I've interviewed over 50,000 people about their hot water use in the last 25, 30 years. And guess what? Pretty much everyone in every group wants hot water to arrive within 5. In order to have hot water arrive within 5 seconds, there can't be more than 2.5 seconds worth of cold water sitting in the hot water pipe. Now, what's 2.5 seconds in volume? Well, it depends on the flow rate. So it's calculable and it's estimatable, and I'm going to tell you it's hard to build because we've tried building it, and it's hard to get that close to fixtures without doing lots of funny things to the main plumbing. And of course, all the architecture that you get in order to design buildings with ends up being where all the fixtures are really close together in a cluster, right? No, we often end up with fixtures spread to the winds of the building. I think that the architect loses their license if they don't put the water heaters as far from each other and the fixtures as possible. Right, Shannon's got the right idea. Look far into the distance to see the fixture. And so I think that that's a problem we have, and it's an architectural decision. So we evaluated the effect of taking the typical floor plan in single family residential, where the fixtures are far from the water heater and spread across the building, at about 75–80% is a pretty good average for single story construction in California, where we did the analysis. And we compressed it to 15%. So not perfectly close, not exactly touching each other, but a much smaller percentage of the envelope was surrounding allocated to the hot water system, water heater and hot water fixtures. And that change saved $1,000 to $2,000 in first costs for building the house. That's a pretty good number, right? By virtue of good choices in design about grouping your wet rooms closer to each other and to the water heater that serves them. We came up with an idea that we implemented in that design for the mechanical room, taking up approximately 24 to 30 square feet of floor space. And we put it in the envelope because we could, because we're going to change technologies and all that kind of stuff made it possible to do it. And we use space, it's only 24 square feet. It's not that much space. Okay, it's expensive space. Yeah, so what? It's expensive to run your ductwork overhead and come back down again and have it freeze and cool and all that stuff too. It's just not obvious. So we talked about it and worked out to be $1,000 to $2,000 per single family dwelling by doing that. In apartments, they're already smaller than most houses are. So the distances between things are shorter, but I have seen 2-bedroom, 2-bathroom apartments with just as much plumbing in them as the same size house would be, separated and detached. Right? And so we have to think about the location of the wet rooms in relationship to the source of hot water. And the way you do that is to reduce time to tap and think about the volume in the pipe. We need water efficient floor plans, and we need the ability to use smaller diameter pipe than is typical. This chart shows you in green what the American Society of Plumbing Engineers thinks is acceptable time to tap performance. And they use 1 to 10 seconds. And obviously that depends on the flow rate. And all of my design work is related to 1 gallon per minute on the hot side. If you tell me you're putting in half GPM aerators or less, I'll tell you to go down in the sizing. I'll go down to 1/4 gallon per minute if it's less, but pretty much everything that I see today and what I foresee in the distant future, even the 50-year future, is on the order of 1 gallon per minute, hot or cold. So the hot water branch lines, or the twigs as I call them, have to be pretty short in order to get hot water to arrive within 10 seconds. And if you look over here on the left, research done by Carl Hiller and validated recently by Yanda Zhang, shows that it takes 1.5 to 2.5 times the volume of water that's in a pipe before hot water comes out the other end of it. And that means if you do the calculation for the pipe volume to get to 8 seconds, you have to actually cut that in half for the hot water to arrive within 8 seconds. So it turns out that at a gallon a minute, it's almost exactly equal to 1 ounce per foot, or 1 second, right? 1 second per ounce. It works the same way. And so it works out to be a pretty simple number. You don't want very much. So let's see. Shannon and Sean and Mark and Zach, how tall are you? In feet, please.
5'10" and a half.
6'2".
6'3".
6'3". I heard something too. 6'2".
5.7.
Okay. And
5'10"
Sean?
and a half. I'm
Oh, that
shrinking.
half matters now, right?
Oh, always does.
Yeah, I get it. So it turns out we're all about the height of 1 cup of water in 1/2-inch plumbing. We are about 8 ounces worth of water. And so if you want hot water to arrive within 8 seconds, you can't have more than a cup of cold water in the pipe. Now work backwards. 1/2-inch pipe is 5, 6, call it 6 feet, roughly speaking. How close does your water heater have to be to your fixtures? Well, a cup. How about a recirc loop? Not much, right? This is a tight constraint, but it's a good goal. So I always work with it. If you're allowed to use 3/8 tubing, you get more length, but you still don't get more volume. It's just length that you get. So when we go into details of how to do it, we'll come to some of the discussion about specifically how. Now, we can also measure time to tap, and that turns out to be pretty interesting. This is my friend Pete Skinner's hand in here, and he put a meat thermometer in there, and he measured what came out of the tap. And you'll notice that it's not very hot to begin with, and then it starts to climb. And as it starts to climb, you now know that that's the volume of water that's in that pipe. If you do a back calculation, you'll figure out that that's the volume. And then it has to rise up to the acceptable hot water temperature. And my question is, when will you get in the shower? I don't take cold showers willingly anymore. All right. So I'm in the 100 to 105 degree range up here. Now, have any of you ever taken a shower with your significant other and noticed that they need a different temperature than you? And when you were dating, it didn't matter? Okay. So this is, we're looking for something in here. Well, that took another 5 seconds to hit that number. Okay. 6 seconds. So it's 1.5 times the volume in the pipe before hot water got there. You got it? This math proves out every single time we test it, it's 1.5 to 2.5 times. 2 to 1's a good guess. All right. And then I have a question for you. This is a shower head situation. This gray line is the normal pressure flow curve for a hole with pressure behind it called a fixed orifice. That's what everything was before the year 2000. There were holes and there was pressure. If you have high pressure, you have high flow. If you have low pressure, you have low flow. If you have zero pressure, guess what? You get nothing. And so the question is, where on the curve are you? And if you're at 40 PSI, you only get 0.7 of what the shower head was rated at 80 PSI. Well, if you didn't like 2 gallons per minute, you are not going to like 1.4. But if you're down around 20 PSI, you're going to get 1 gallon a minute. You're going to start screaming bloody murder, right? So the manufacturers of shower heads asked their supplier of the flow regulators to come up with a better idea, and they did. This green line is a pressure compensating orifice in a shower head, and it gives you much higher flow rates at a much wider range of operating pressures. Okay, and since the plumbing codes limit us to 80 PSI going into our buildings, everything is at a deficit. It's always on this part of the curve. Oops, sorry. Back, go back. Right, everything is always somewhere back in here, and people complain. So if you put a pressure compensating orifice in, you're going to be close to the green line for showers. Everybody good? All right. Now this is for faucets. And what you can see on the right are different faucets looking in as though the water is hitting it. And you can see that some of them have this little O-ring in them, right down here. That tells me it's pressure compensating from this manufacturer. And then they have, that's the single core is the green line. The dual core is the yellow line, the gold line. And I want to go for the gold because customers want performance and then be efficient at doing it. And this gold line gives you flow rates that are almost 100% of what it was rated for, all the way down to almost 15 PSI. If you only have 15 PSI, other things are in trouble in your house. So you've got to pay attention anyway, or your apartment building. So we want these in our buildings, and we want to have single core, not the ones that you see over here that don't have any at all. All right. This is all about customer satisfaction. It's all about time to tap. It's all about making the end user happy with our experience. And then if you design the plumbing right and you put the wet rooms close to each other and to the source of hot water, even in an apartment building, you end up with smaller loops. Smaller loops mean less heat loss. I think it's in multifamily buildings. I also think it's a requirement that the mechanical room be in the far corner on the first floor in the basement, and the furthest fixture is upstairs, however many stories on the far end of the building. Isn't that the way it is, right? That's what we get. We don't get that design. Somebody gives it to us, but fix it. You know, you can put lipstick on a pig, but it's still a pig. You got to do better, right? We have to start building better animals, if you will. So we measured the operating losses of a recirc loop and the uses of the tenants in this apartment building, 35 unit apartment building, and you'll see that the losses were bigger than the uses. They were 50% bigger. That's terrible, right? Our new design, the new building we built based on our work for right sizing, and we couldn't move the water heater, but we could move the plumbing. We got it down to 20%. So it's 26% of the uses. That's a pretty good deal, folks. Right? That's the kind, look, it makes no sense to have losses bigger than uses. Right? Losses, uses. Losses should not be bigger than uses. Why would you want to waste the energy or the water or anything else? So now let's move on to what we learned this past year. That's what we went into last year with. We knew all that stuff. All of that made sense to us. And then we started an exercise to right size the plumbing. And you can see here it saved about $5,000 for this apartment building we're discussing. And it's a 92 unit apartment building, so it's about $54 per apartment. Okay, everyone got it? That's pretty good. Like $54 per apartment's like money here, right? It's a big building. But look what happened. This is two examples. This is Meadows Senior Facility Phase 1 in upstate New York. Building E is the one we've been measuring. It's senior living. It's 1 bedroom, 1 bathroom. Laundry rooms are shared on each floor. There's a kitchen in each apartment. No bathtubs, just showers. This is the Phase 2 construction. We got asked to participate when they'd already poured the foundation. So nothing could be changed in terms of floor plan. We missed that boat, right? We can't fix that at all. This is a 24 unit apartment building also in upstate New York. And this is mixed family housing. So it's not just seniors, it's all different age groups and families and such. So I've just shown you a 24 unit apartment building and a 35 unit apartment building. And I've looked at a 40 unit apartment building. I want to know what you think the peak flow rate is. Shannon, what do you think? Sean, Zach, Mark?
5.
5 gallons per minute at peak for the whole building or per apartment?
Per
Per
apartment.
apartment.
Per apartment. I hear Mark, you second that? Shannon, any ideas?
Sean and I are holding with 5 per apartment at peak.
You know, I'm gonna change my answer. Price is right. 1. Going with 1.
So you're going to go with 1 gallon per minute per apartment. So 24 gallons per minute for 24, 35, etc.
Final answer.
So we're at either
Okay.
24 gallons roughly, right? Or
Yeah, 24 to 120.
or 119.
Yeah. Okay. There you go. So this graph that you see here is the red line is the plumbing code for upstate New York. And it says that for hot water, you should expect it to be about 50 gallons for the building, a little bit more than 50 gallons per minute at peak. So sort of like not quite 1.5 gallons, sort of like the shower is on in every apartment is what that works out to be. Okay. And then ASHRAE has a method of sizing for apartments and houses that brings the number down to about 30 gallons, so almost one. There you go, Sean, there's your 1 gallon per minute number. And then there's water demand calculator version 1 and version 2. And when we built the buildings, version 1 was available and version 2 is the one that's out now. And that predicts about 14 gallons per minute, and that predicts a little under 10 gallons per minute. And that's what we measured. We've never measured 10 gallons per minute, let alone these other numbers. So this is on the order of 1/10 of a gallon per minute per apartment, much lower than we would ever guess, and certainly much lower than the code suggests. And so one of the tasks I want our community to undertake is to start measuring flow rates in buildings that we're designing and building. Let's go back and measure some we've just finished building. Let's go in and do a quality assurance assessment to see what happened. Because if we keep finding numbers that are down here in this bottom segment, less than 10 gallons per minute, no matter what the size of the building is, why are we sizing for the red line? It really makes no sense. And if we want to make our buildings better, we need to make the piping right sized, whatever that might be. This is another view of the peak flow rate for Meadows, 2.85 gallons per minute hot and a little under 5 gallons per minute cold. We've gone back to this building several times. We always see numbers like this. We do snapshots for a week, 2 weeks at a time, and we've never seen peaks that are higher than these. And notice that half the time, the water flow rates, hot or cold, are less than a gallon a minute. If you put in pressure compensating aerators, you don't really care if there's a higher peak because the customer won't be significantly worse off. They won't notice it. The fixtures will continue to operate. Okay, all of this is the way we have to start thinking in order to make better buildings. This is looking at Solara. There's about 38 people living there. It's mixed occupancy. I think these actually have tub showers, not just showers. I'm not certain off the top of my head. And we have higher flow rates, but there's more washing machines too. I don't know. I don't know the exact reasons. All I know is it's pretty small, under 5 gallons per minute. You see these little numbers out here? When we look at them in detail, they're seconds long. The 99th percentile is not the absolute peak. It's all but 1%. When we design heating and cooling systems, don't we do that for 99th percentile too? Why would we do any different here? So my friend Pete had an epiphany. If the flows are so low, why are the pipes so big? You know, there's engineers and there's rules, and everyone's got a design method. Well, they claim they have one. And so they follow certain sets of rules, and you end up having to estimate peak flow rates. You then estimate pipe sizes. That information goes over here to estimate peak hot water, hourly hot water demands, and you size your water heater. And I have a question. What methods do you use? What methods does our industry use? This community of passive house use? I don't know, right? It's probably one of these, maybe more than one of these.
It's really interesting. I love the questions flying in, and I really enjoy it when Gary rhetorically states, "Does anyone know how they actually measure these?" Right? He wants us to answer, but he wants us to not have to answer. And I just love that.
Yeah, I'd love to know what he's using to monitor this usage over time, especially for the multifamilies.
Yeah, and so his request, right, is that each of us measure the flow. So I think in the overtime, let's get into who would be willing to do that, to go back to a building you just finished or a building you finished at another time, record the flow rates and pass it along. If you're willing to do that, I know they would love the information. So perfect. Gary's back.
Right. I'm back. It didn't take very long. It's pretty quick. So to answer your question quickly about the flow rate measurement, we're using strap-on flow meters that are accurate. We can measure 1 second data if we have enough buffer to store it. But we're testing whether we can get away with 1 second, 5 seconds, 10 seconds, 1 minute. And we've assessed it and said our 1 second numbers are not, 1 minute numbers are not all that different than the 1 or 10 second numbers. And so we've got fairly good equipment, and it ain't free to measure the stuff. On the other hand, all of our new buildings should be designed to put in flow meters as part of the process. And I would recommend we make that part of our warranty. Okay. So let me see, are we sharing still?
Gary, real quick with that, a flow meter to install in line with the building.
Yep.
What something like that run? Target price?
Hard to answer exactly. We're working on a package that I'm pretty sure is going to come in under $1,000 for 2 of them. Because you need 2. You want hot and cold. We always care about the cold water flows, the hot water flows, because we were worried about the energy. But we need data on hot and cold ultimately to right size everything.
Material cost and labor cost is offset by the right sizing of the pipes. Perfect.
Absolutely. Yes. So here we go. Let's see if I can get this settled out here. All right. So, whoops, there we are. So the question is, which one do you use? I don't know. It's one of these, right? The water demand calculator is what we used for the buildings in upstate New York, and the design for the buildings that we're going to talk about today in Seattle. And we used version 1, which you can see over here. Version 2 looks a little different. It now has the ability to toggle between single family or single unit and the whole multifamily building. And it's very clever, and it accounts for things, and it's much closer to reality than any of the other curves we've ever seen. And so what do you get in benefits by right sizing? This is a 92 unit apartment building with 1 bathroom, 12 washing machines, a kitchen in each apartment, and the plumbing code says to expect 127 gallons per minute and a 3-inch main. And the version 2 of the water demand calculator says, nah, it's going to be more like 14 gallons a minute, and it's going to be a 1-inch main for 92 units and washing machines. Nobody believes it. It looks too small. Even to me, it looks tiny. Okay. But if the flow rate's only 14 gallons per minute at peak, why do I need a 3-inch main? I don't know. You don't. And look what we got rid of. This is like for like feet. Everything is the same. We redesigned the plumbing based on right sizing. And we were able to save almost $5,000 in first costs of piping. That's just the feet of pipes.
Time for people not listening that are always stuck on cost. How much did we save?
$5,000, $54 per apartment in hard cost of pipe. Okay. Now so we keep getting this iceberg gets bigger. Now we get to right size the rest of the plumbing. What do I mean by that? The first numbers were just the feet of pipe, not the elbows, not the T's, not the couplings, not the valve, not the valves that go in, not the pumps, not the balancing valves. Everything got smaller. Oh, I forgot. The pipe insulation now has a smaller inside diameter, so its cost went down. Okay. Oh, and I suspect it saves a little bit of labor because it's easier to move smaller pipe around than fat pipe, right? It's just a little easier to do. All right, so we save another, didn't calculate this number exactly, but I'm pretty sure it's on the same order of value as the pipe, okay? Now, we got to right size the water heater. At the project we did in upstate New York, the water heater size went down from 50 gallons per minute to 12 gallons per minute, a factor of 4 reduction. We got to right size the water heater 75% smaller too, and we did. And that saved us over $20,000. So in this case, the plumbing code says it was supposed to be 105 gallons per minute in this 92 unit apartment building. Water demand calculator says 11. That's a factor of 10 reduction, 9 or so. I figured that was worth at least $30,000. I don't know. We didn't actually calculate this one yet, but that's like a lot of money. It might be more than that, but that's like money, okay? And with this effort that's underway right now to electrify everything and put heat pump water heating in, we need every penny we can get because those systems cost more than we're used to paying for water heaters, right? So there you go. Then the next thing we did, This is around Seattle. This is great. So if you're in Seattle and you build this building, your installation and connection fees for a 3-inch main, they don't have it here. It's $24,000. If you use version 2, you're a 1-inch main, you get to save, what is that, about a $16,000 reduction in cost, first cost, right? That's like money. And then if you're in Skagit County, which is just outside Seattle, they have rather higher fees and you get to save like a lot of money here, right? What does that work out to be? $67,000, almost $70,000. That's like serious money, folks. $740 an apartment. That's a pretty big range. So it matters where you build. All right, where did it go now? Come on. And then finally, you get ongoing operational savings. This is just the water savings. Do you realize there are some energy savings from all of this too? All right. And there's some real water savings because of using less water. This is just the fixed cost of water operations, $150 to $300 a month. Okay. So in summary, what do you get for all of this? Focusing initially on time to tap, we increase customer satisfaction and save a bit of cost in first costs in the apartments themselves. Right sizing the plumbing gets us $5,000, the rest of the plumbing another $5,000, the water heater another $30,000, the meter gets us these numbers, and we get total savings on the order of $60,000 to $110,000, and first cost savings per apartment on the order of $600 to $1,200. Operational savings, $1,800 to $3,600, could be more if you count all the other things that the use rates we haven't quite accounted for yet by saving some water and energy in the building itself. All right. So then the question is, what else do you get? I want to talk about this for a minute. Look, we have to worry about commissioning our buildings. It's part of our normal practice as passive house in our community to do this. And it begins with the design. You have to do regular site visits. You have to inspect. You have to make sure people build as intended. Then you want to verify at the end that it works. And quite frankly, commissioning for the complex system should continue for the life of the building. It shouldn't just stop at the end of construction. That's why I want us to design in the ports to do the measurement so we can easily add it later. The water costs, we talked about that already. Less volume means less time, less cost, everything else. The sewer charges are often proportional to the water that's used. Less water means lower sewer. And energy, if you cut the volume of the water pipe in half, you cut the diameter in half, you roughly cut the volume in the same length in half for all materials and sizes that we're interested in. Which means that at the end of the day, when all the pipes cool down, if they're one size smaller, you will lose half as much energy. Well, that's a number. I don't know how big that number is. Depends on how many feet of pipe you got. But it's a big number. And because they're smaller, hot water gets there quicker. And the loops, as we talked about earlier, can be more efficient and lose less energy, all of which are necessary to meet the passive house requirements. And then I want to talk about increasing customer satisfaction. It all starts with the floor plan. We need better floor plans. Designed for modern pipe and fittings. It turns out that the data we're using were published in the 40s, and for pipe fitting losses, pressure drop losses, the research was done in the 1890s. We want anti-scald tub and shower valves, and they have different pressure drops. So that if you look at a list of, the bid spec says yada, 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 or equal, they're not equal. And when a future webinar, we'll talk about how those differences and what they look like. And then we've already talked about pressure independent faucets and shower heads. You decide the flow rate you want, and then you specify pressure compensation so that the customer wins with the decision.
Gary, thank you so much. Part one of a series for sure. If I could take everyone's temperature for a minute, I hope everyone enjoyed this. Sean, you're just grinning ear to ear.
I try to take notes. My hand got too hot, so I gave up, and I've been trying to take screenshots through it. So like I said before, I'll be watching the video in a couple of days when it gets posted, because there's just too many good nuggets here. So great job, Gary. I think, Shannon, let's get into the questions, because I think Kevin's still on a fire call. So
Hey, Sean, with that, for the notes, I'm the same way. I do take the screenshots, and you'll see that loading up on Instagram and LinkedIn in between screenshots, though I am trying to keep up with all the great comments from Michael. So Shannon?
Absolutely. Not only the great comments from Michael, but we had a flurry of activity in the chat. And a lot of it was answered by some of the other attendees. So we definitely had a combination of the exploratory questions and the clarifying questions. But we are going to start off with a question from Francis. If you had any questions, Francis, you can unmute and ask your question. And if you feel like they were all answered by Michael, then we'll move on to Justin. Francis, are you there? Would you like to ask your question? Well, Francis must be feeling shy. So how about Justin? You had a couple of questions. Would you like to unmute?
Yes. Thank you for the presentation. It was quite excellent. I know that a lot of the discussion was really just about the designing the entirety of the system. My question now goes actually to water efficient shower heads. Are you familiar with the Nebbia shower head? It's like a atomizing shower head. It's like supposed to give you like a spa-like experience, but it's supposed to use like a very tiny fraction of the water we usually use.
Yes.
And I'm just wondering how that affects the pressure calculation that you were talking about, something like that.
Well, I haven't actually measured one, but I can predict what I think it's going to look like. But the website before Nebbia got purchased by Moen. And so now it's Nebbia by Moen or something like that is the way it's marketed. But when it was still Nebbia, they had literature that described that the temperature drop from the shower head to the person would be close to 20 degrees because of the small droplet size. A typical shower head of the other type that we're all used to is 1 to 5 degrees per foot, and we're about a foot from a shower head. So did you know that short people need hotter water? Because they're further from the shower head, right? And so the Nebbia tells us in its literature that the temperature drop is 20-ish degrees for that same distance, which means the water heater needs to be set higher or delivered hotter to the fixture in order for it to give you the temperature you want in your shower. Okay? So the pressure drop, in order to create small droplets, one could anticipate more pressure drop, but they might just do it by spreading it out through more orifices, right? So you don't necessarily create more pressure drop, you just spread out the spray pattern. I was having this conversation with somebody earlier today, not related to this call specifically, but about this problem of shower heads. Some years ago, I purchased 2 shower heads from the same manufacturer, one with 4 nozzles with lots of little ports and one with 8 nozzles with lots of little ports. Okay. And the question is, which one has greater pressure? Which one feels like a harder spray? The one with 4 ports or the one with 8 ports?
4, right?
Yeah, because it's coming out a fewer number.
Right.
And so I like a harder shower. I don't know what kind of shower you like. And I don't think it's easy for consumers to look at a shower head and figure out what the experience is going to be just by looking. So you take it home and try it, then you hate it, then you bring it back and you do it a couple times and you give up. I think we need a better method than that. Okay. Does that, I think it has to be tested. So we set up a lab to test the pressure drop of shower valves and pipe and fittings. We can easily test the pressure drop effectively through the shower head itself. It's possible. So it needs to be done.
And then the other question was in undersizing the pipes like you were describing, do you have any regulatory pushback from like building inspectors and such?
So I'm not undersizing, I'm right sizing. The code is oversizing. Let's be clear about our relationships here. Okay. And yes, of course we get pushback. Didn't they get pushback for the first building you brought to them says, I want to do the insulation this way?
Yes.
Okay, so this is normal. Change is tough.
Mhm.
And what happened in upstate New York, where we built these, the inspector said, okay, why? Because the engineer of record has permission in the plumbing code to design the system using nationally recognized techniques. And Appendix M from the Uniform Plumbing Code is the start of the water demand calculator that we used. If you want to look up water demand calculator, go to IAPMO, IAPMO, comma, water demand calculator in Google search, and you will find it. It'll take you to a home page from IAPMO called We Stand, and you can read all about it there.
I threw that in the
Okay.
chat as well.
Thank you. I'm not able to do much with the chat given where I'm sitting at the moment. Thank you. So that methodology comes from a code change proposal to We Stand that became part of the 2018 plumbing code, Uniform Plumbing Code, and it's a model code that's usable around the country. If you happen to be in IPC land, you can still use references from ASHRAE and other sources. You just have to explain it. When they went to the went to the water supplier to get the meter, they said, you want to do what? Because they were expecting to put a 3-inch meter just like they did in all the other buildings. And in this particular case, we went down to 1.5 because this was a year or so ago and we didn't know as much as we know now. And you can just imagine what the conversation would look like. Some version over, you've got to be kidding me. But you know, the engineer of record went through the process and explained it all. And everyone was happy. And they said, okay. So yes, Justin, there will be pushback.
Thank you.
Thanks, Justin. Great answer. Thank you so much. We have a question from David Solomon. David, are you out there? Would you like to unmute?
Yeah, hey there. Thank you. Gary, thanks for your time tonight. I have 2 questions for you. One, how do you specify the dual performance, or
The dual core aerator?
The dual core aerators.
Right.
Then,
So, yeah, okay. I'll go ahead. I'll wait. Go ahead with the rest of your question.
Well, my other question was, do you have any examples that you can show us of architectural changes as a result of, you know, your process and your intervention? You know, have you, you know, particularly for multifamily homes, right? There tends to be, I mean, you don't really have to reinvent the wheel over and over and over again. And so I'm sort of curious if there is a particular, I don't know, whether it's a layout or a, you know, is it like a, you know, decentralized or semi-centralized approach that you like to take? And yeah, and really if you had any kind of examples of like, here's what we started with, and then here's where we ended, and these were the changes in this particular instance, you know, that resulted from this process.
Absolutely. So the first question first. When you specify, so the dual core is currently only available in faucets, not for showers. Single core for showers. And what you do for showers is you specify yada, 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 yada at 1.8 gallons per minute, and you specify PCA, pressure compensating aerator. And each manufacturer probably has a slightly different listing for it, but go to their website, look it up, and then you want to say, I want PCA. Sometimes they say WaterSense. That's not a guarantor of it, right? But you want to specify PCA, all right? And then the second question you asked, and so for faucets, you can do dual core. And the primary manufacturer of all of these aerators for faucets and showers for the US market is Neopearl, the company's name. It's sort of like Intel inside, it's Neopearl inside. That's Neoperl. They're based in Connecticut. I think it's Waterbury, Connecticut. Sorry. And they make this stuff for all the main brands in the United States. They make them for most of Europe too. All right. And so they make all of them, the fixed orifice, the single core, the dual core. If you ask for the California faucets, because I live in California, they're all 1.2 gallons per minute. And they started out making those aerators with dual core. So you can get dual core, and it's like SC or DC PCA. Does that make sense?
Yeah.
So pretty straightforward.
Great.
So the second question was architectural design. The single best floor plan I've seen for single family detached went from an 80%, 75 or 80% of the floor area of the dwelling related to the hot water system in 3 stages down to less than 1%. They have one plumbing wall in the middle of the dwelling somewhere. And so that's pretty darn good. Now, you might not like the layout and the floor plan so much. Okay, but under 10% is a pretty darn good start, right? So let's relax the restriction. Well, it turns out this is for Habitat for Humanity in Stockton. And the project manager figured out that he needed simpler stuff because his labor force couldn't do anything complex. He's got all volunteers. They show up on Saturday. He doesn't know what he's going to get. Right. And so he figured out a way to make it happen. And, you know, his second worst case was 3%. You know, that's pretty good. Okay.
And so for, you know, for a habitat, right, I think we're talking probably about, you know, multiple single family homes, right? As opposed to a larger, you know, you know, a larger multifamily complex.
I get it. So your question, multifamily, is a good one. The best I have seen so far is from, what's his name? Tim McDonald in Philadelphia.
Yep.
And the reason that is so good is that, as he describes it, he put the plumbing following the vent stack rules. All fixtures are no further away from the vent than allowed with one vent. So he's got a stack of apartments, 7 tall. It's 3 stories, so it's 4 stories, 1 + 3 on each of the other 2 floors. And all of the fixtures in all of the apartments are less than 10 feet from the stack. Well, that means they're close. It's not 5 seconds to hot water. It's 10 seconds. That's still better than a minute. I mean, come on. We even in apartments wait a long time. So that's the best I've seen so far. The best 2-story dwelling I've seen, single family detached, is the NIST net zero energy home that they built on their campus. I think most of us know the architect. It's Betsy Pettit. And, you know, she gets props for designing it so that everything is within 15% of the floor area of a 2-story home. That's pretty darn good. Somebody wants me to tell people about Tim's pipe and pipe hot water return, which I will do at some point, but not in the middle of this question.
Great. All right. Well, thank you. I appreciate it. I'll let
so when we go into details in future webinars, we'll go into how some of this gets done and what it looks like. You are absolutely right, David, that I think that it's a requirement for architects to design every new multifamily as though they'd never done one before. And all sites are unique. And you know what? That's just not strictly true. I believe firmly that there are designs that are efficient to build and operate, and we should stop doing stuff that isn't. And so we just have to, like, we're not going to do that. We're going to create cookie cutters. They're going to be nice cookie cutters, but we're going to create stuff that's repeatable time after time after time. So performance is repeatable. It's one of my pet peeves. So
you know, the flip side of that is that there are so many people, and I'm going to pick on engineers in particular, that only want to do the same thing that they've done over and over and over again. And it can be very difficult to, you know, get them to try something like, I'm familiar with, you know, Tim's pipe within a pipe, and I'm familiar with the project that you mentioned. You know, and I just like, what's your recommendation for, you know, other than sitting my engineer down and showing them this webinar, you know, what's your recommendation for just, I guess, engaging with engineers in particular and trying to work with them to get them to, you know, increase the efficiency of the systems. Obviously we want to do this architecturally and we're already on board with that, but it's still, sometimes I just find it is such an uphill battle just trying to, you know, even just get the engineer to do the, you know, no, it's not going to be a centralized gas, you know, heater with a gigantic recirc. You know, I mean, that bar is just so low. You know what I mean?
So you've asked a very interesting question that I would actually like to put into overtime because it's going to be a longer answer. But fundamentally, the most successful experiences I've had to get people to start to change their way of practice is to stop trying to make them and find those that want to.
Sure.
Okay.
Sure.
That's a
Because
great
it's much
answer,
easier to
Gary.
direct somebody who wants to move where you want to go.
Yeah. It's
Now,
not always up to me, but yeah, I hear you.
I get that. So having said that, my most successful experiences in converting a team to do a better job is to go do a walkthrough of a project that's under construction. I'm looking at the plumbing, so I'm not looking at everything else. But I require that the team include the owner, the decision maker has to be in the room. Okay, because I don't want to have to explain it 3 times. And I don't want underlings to explain it to the boss because they'll never translate it right. I want to be the person taking the hits. So the owner has to be there. The decision maker has to be there. I want them to bring their key people on their team. So I want structural engineering. I want MEP if there is one. I want the architect there. I want, yes, like Sharad. I did walkthroughs with Sharad. And so what we do is we take the team through the building and we assess what they call normal. And from my point of view with the hot water systems, I follow the water through the building. And I say, before we get started, we're going to ask a question. How well is the plumbing built from the perspective of getting hot water to the fixtures quickly and efficiently with the least pressure drop and the least waste? Okay. And we're not, no red tagging today. We in fact bring inspectors on these jobs. And everyone just laughs because you can't red tag. You can talk about it, but here we're today to see what we've approved already. What's going on? What's normal? And we walk through the building and ask, how long is it going to take to get hot water to every fixture the way it was designed and built? And we point out that some buildings have beams in the way. And I look to the structural people and I say, why is that beam there? Oh no, looked like a good spot. Could it have moved 10 inches? Yes. You know what that does? They don't know the impact of their decision making, right? And so if you can move it a foot or 2 feet, you just save 50 feet of plumbing. That's a good deal. You probably save 50 feet of ductwork too, right? And so the walkthroughs turn out to be a very, very useful, non-confrontational way of getting more people on the team on board. And then if you have to have the conversation, if you're in the position to do it, you go to the owner and say, we need people on this team that are willing to meet your vision. And you can pretty much interview everybody on the team and say, are you willing to help us get there? If the answer is no, you say, thank you very much and find somebody else for the team.
Gary,
Eventually they'll come up.
Great advice. And I'm going to stop you real quick right there. And I am fully going to hold you to answering that question in more detail in the after hour. And David, thank you for those questions. They were fantastic. We're going to hand it off to Zach to wrap up our first hour, and then we're going to head into the after hour together. Gary, get your mentor ready. We want to hear about who is inspiring you to learn this stuff and share it with us.
All right, thank you, Gary. Fantastic. This is pretty mesmerizing stuff. So we really appreciate you sharing it with us all today. And none of the work that we do would happen at the Accelerator were it not for these fine organizations, our sponsors. So a big thank you to our founding sponsors, 475 High Performance Building Supply, Baxtingwe Architects, Mitsubishi Electric Train HVAC US, Partel, Glavel Foam Glass Gravel, Minutair All-in-One HVAC and Dehumidification Units, RDH Building Science, Rockwool North America, Stocorp, and Zola Windows. Our champion sponsor is SIGA. Our stakeholder partner is NYSERDA, the New York State Energy Research and Development Authority. And our patron sponsors are AeroBarrier, BR+A Consulting Engineers, Brennan Air Tightness and Insulation, Inotech Windows and Doors, and US Engineered Wood, T-Stud. So thank you very much to our sponsors. On the Passive House podcast, we have a new episode up right now with Jose Sosa Rueda, who is the Panama chapter founder and lead for the Passive House Institute Latin America. And he has a great conversation with Matthew Cutler Welsh about Passive House in Panama and Passive House in hot and humid climates. So check that out, please. Tomorrow, Global Passive House Happy Hour will feature the presentation with Jeremy Huerta, Paul Warwick, Scott Kennedy, and Luke Hahn about the Peak, which is a multifamily project in Vancouver, BC. So we get both the builders and the designers' perspective tomorrow. So please join us for that. Next week on Construction Tech Tuesday, we're going to Eastern Europe. We have Marius Sofletti, who will be presenting about the largest passive house building in Eastern Europe and the construction tech that went into that project. And our happy hour will have Cycle Architecture and Planning. So Caitlin and Tony from Cycle presenting about the Crown Heights Passive House Project multifamily building in New York. And then on Thursday, June 24th, we have Centering Equity in Passive House, which will be co-presented by Astrid County and Johnny Rezvani. This is a Passive House community workshop. And it's a presentation and workshop to offer a practical path to companies to either begin the discussion or improve upon existing diversity, equity, and inclusion initiatives within their firms. The presentation, which was developed from the Centering Equity in the Sustainable Building Sector initiative of NAACP, asks members of the Passive House community to challenge themselves, their companies, and organizations to take on self-identified commitments which build up the next generation of Black, Indigenous, and people of color professionals in the design, engineering, construction, and management of the Passive House movement across North America. So we hope you'll join us for that on June 24th, 7 to 9 Eastern, 4 to 6 p.m. Pacific. And that's it for me. Thank you.